Have you ever pondered the true essence of a function having a limit at a point? The epsilon delta definition, a fundamental concept in calculus, provides an answer to this intriguing question. It's a formal way to define what it means for a function to have a limit at a particular point. But don't fret. We'll break it down into digestible pieces. Scene script. Picture a function f(x) and a point A in its domain. We assert that f(x) approaches a limit, L, as x nears A. But here's the catch. No matter how close we get to A within a certain distance, delta, the function values f(x) must get arbitrarily close to L within a certain tolerance, epsilon. Sounds complex? Let's make it simpler. The Greek letters epsilon and delta represent these tolerances in the definition. For every epsilon greater than 0, a delta exists that is also greater than 0. This delta is so that for all x in the domain of f except for A, if the distance between x and A is less than delta, then the distance between fx and L is less than epsilon. This abstract statement encapsulates the intuitive idea of limits. As we inch closer to the point A, the function values draw nearer to the limit L, no matter how small the tolerance epsilon is. There are some key points to keep in mind. Epsilon signifies the desired level of closeness to the limit L. The smaller the epsilon, the closer we want the function values to be to L. Delta, on the other hand, is dependent on the chosen epsilon. For each epsilon, we must find a corresponding delta that guarantees the closeness condition. Finally, remember that the definition excludes x equals A because the function might not be defined at that point. In a nutshell, the epsilon delta definition of limits is a precise way to understand the concept of limits. It might appear daunting at first, but with a little patience and understanding, it becomes a powerful tool in the realm of calculus and analysis. So the next time you are faced with a limit problem, remember the epsilon delta definition and tackle it head on.